Hello everyone, this is Bradley. So today we're going to do this knitting animation. Knowing that knitting animation is so complex because there are so many different variations, patterns, approaches to do that, you can find all sorts of references from other software. Or even within Blender itself, people come up with different ways to do that using different tools, add-ons, versions of Blender. In the past, I've posted a tutorial using field prototype. However, as time goes, so many things have been changed. The old tutorial is no longer replicable. Today we're going to do one of the variation of knitting animation, which is very good looking. However, honestly speaking, I think it's of less practical use. I cannot come up with a nice way of using that other than just what you have seen. I still posted this tutorial. Maybe you can find some good use of that. So let's start. So here we're in Blender. Let's go to noding. As always, I'm going to use the presets from my preset library. You can download them for free from the link in the description. I want to firstly talk about the differences in different approaches. So in the past, while making the tutorial, you can find the method I was using is to create a single unit first by whatever methods. You can model a single unit, or you can do whatever you want, but basically it's a single unit and you instance it. This method is less controllable, but it's really good. Today, however, we're not going to use this single unit. We're going to use a math function to do the work. So let's start with the curve linear presets, or you use curve line when they resample that. I'm going to turn off the center and the step so that we can control the length of this line. Let's just to make it a little bit clear, I'm going to take a bevel curve to add some thickness to that. And we need a set position, and finally add sine wave on the top of everything. Let's plug these values to be pi so that we have a half of phase of sine function. Let's take a position and separate x, y, z. And we also need to combine x, y, z. And we do something with the offset so that we keep the original position. Sine function is pretty simple that you may think, let's just take a math node and there's a sine function. However, in reality, sine function is more complex than that because of many parameters that you need to consider. For example, a frequency needs a multiply, a amplitude needs another multiply, and phase needs an add. So basically at least the 4 nodes that you need to take. And we're going to do the same function for all these kind of 3 axes. I'm not going to replicate 12 nodes for the function. That's why I'm using a single preset which is called sine function. Plug the y. I think that's the single best answers. And take a frequency to 2. So 2 pi, we have a length of pi, and we have frequency of 2. So we combine them together, it becomes 2 pi. 2 pi means a full phase of sine function, as you can see, a single up and down. If you take that to 4, then you have up and down, up and down. Okay. So for y-axis, we only need a single phase. However, we're going to change something with x as well. So for x, what I want to do is that I want this point to go to left, that point goes to right, this point goes to left, that point goes to right. So instead of a single set of up and down, I need up and down twice. That's why I need frequency of 4 plug to x. So immediately we get some interesting patterns. We run out of subdivision, so let's increase the count to smooth out. And then let's decrease the amplitude to negative value, and now you can actually see a very interesting patterns. And let's take another sine function, still use x, and this time we're going to plug that to z so that it goes up and down. Let's take the frequency to 4 as well so that it goes up and down, up and down. The reason to do that is later we can lock all these kind of knitting units together. Here it is just an example of this pi and all this kind of frequency. I want you to pay attention with the relationship between this kind of frequency. So x and z must contains double amount of frequency compared to y. So let's make it more procedural with a value and the math. So take it to 2, multiply by 2, and the product goes to x and z, value goes to y. So right now we do not change anything, but we're going to change this later. This is just an example. So instead of using stop mode, I'm going to take this box so that it goes back to the step mode. Step mode gives us an advantage that we keep the resolution of each kind of points, but as we increase the count, it becomes longer, and we retain this pattern. Okay, and we can increase the frequency, so now we have a nice netting patterns. If you would like to increase the resolution, then you just decrease it. So now we have this kind of patterns. We're going to instance this single unit on the y-axis. You can instance it here, you can instance it there. But because I want to retain this ability of offset, because if I take a vector math and if I scale, you can actually see it goes from straight line to a pattern. So this is a very important part that I'm going to instance at this stage, so that I have the ability to control whether it's a straight line or a curved netting pattern. Let's take another curved linear node, but instead of instance on x, I'm instance on y. Maybe I will use the, I'm not sure, stop or step, but something like that. So now we have a straight line. But why it's straight if we're setting the position? Because we need to realize the instance so that we can actually access all this kind of information. So now we have a compacted netting patterns. It's not really interlacing to each other. It's more like kind of weird whatever stuff. So here what we're going to do is I'm going to change the phase of the sine function for like 1.5. So that it forms this kind of pattern. But on the other hand, this is actually also called cosine wave. So this is the relationship between sine and cosine. And this pattern is basically it. Just to know that there are so many different parameters that you can change. Frequencies, you can decrease it, you can increase it, you can change the amplitude of x and y. There are so many things that can be changed. That's why I hate these things, because you change when you change the others, and they can look just so different as the time goes. So yeah, something like that. I probably will say that's probably it. So let's move on to the next step, talking about how to animate it. Here, let's firstly take this center of the box, so we center on y-axis. And as mentioned previously, by manipulating this scale, we're determining if it's a straight line or a netted pattern. So this is one parameter that we will animate. Another parameter is, let's take a mixed vector. Here, I think this is going to be the vector B. So for vector A, we basically just offset these splines, okay, so that they lifted up skies. Another thing I'm going to do is to deal with the position. Here, let's take a position vector mass, and I'm going to multiply that with 101, so that it looks like a kind of straight line. You can manipulate it however you want, but this is what I'm going to do. And I plug the original position to vector B so that it can expand. So here, if we play these kind of values together, you can actually see how it has been changed. So we need to synchronize the change of these three parameters, and I'm going to put a directional fourth onto it. Let's take a control, which is basically an empty object. Select this empty object, plug the fourth into scale and factor. So now I'm controlling these three values with a directional fourth, and you can see what's actually going on. If you increase the scale, it becomes much softer, and so on. Okay. Sometimes you may not like this kind of obvious whatever stuff. So you may even create additional directional Falloff with all these kind of directional offsets. But that's another story. I'm not going to do it here. Here, this is kind of very boring. So we are going to add some noise. For example, the noise on directional Falloff and the noise on this spline. Adding noise is kind of tricky because I'm going to show you why. So if I directly add a position translate, really it's just a vector mass nodes added to the position attribute. And here, let's take a noise CD. If we plug the factor into this vector x, in low value it may not look anything wrong, but if you increase the scale, you realize there is jagginess on the proximal part. This jagginess is irrelevant to our waviness afterwards. It presents here. It's simply because we offset every vertices, so disrupt a lot of things with our directional Falloff. So basically, the idea is I want to offset each line instead of each point. So here, let's take a capture attribute. And I'm going to capture spline. We can capture a vector, take the position, and plug these attributes to the custom vector. So now we eliminate the jagginess while keeping this kind of offsets. We can change the parameters, distortion, or whatever stuff that you want. It's customizable, increasing the frequency or decrease the frequency. But more importantly is change the scale while we do not have the jagginess that we had previously. The reason this works is because every spline is being offsetted. So yeah, something like that. Okay, so this is one part of noise that we can add. There is a second part of noise that we can add on this offset. So just to take another, where's my offset? Yes, the offset is here. Just take another vector mass nodes and add to the noise reading. So we can plug the colors. Now if the entire noise is put on every part of this spline. That's why it's very ugly. So I want this noise being only restricted to the part which is flying down. So which is related to our directional Falloff. So let's take a float curve. And here let's take another vector mass. Set that to scale. So that by controlling the scale, we can controlling whether this noise presents or not. Let's tweak this Falloff to be 0, 1, 0. So that only when this spline is flying down, there's a noise added on the top of them. In this case, if you play around with the frequency, or details, roughness, distortion, scales. These are the parameters that you can play around. Okay. So basically, yes, this is it. If I were to add anything, for example, you want to evaluate this noise, you can select this object. But it will be affected by the scale of object as well. So instead, I'm going to take the position, translate the position, so that there is an option only the location is affecting the translation, and then we select this object. So it may not be obvious, but it's, for example, like if you animate the X value, then you can see this movement, and then this will be equally true when we're animating this spline. It may not be very obvious, but there is effect that these splines or this noise is flowing with our spline. Okay, and maybe you do not want to create all this kind of organized knitting pattern. So at the end, you just want to create a end result or a more general noise. It's also possible. It's basically, you can add more details if you want. You can do whatever you want, and maybe you can add the same translated position so that this spline is also flowing. So these are just the, just to know that the more settings you add, more nodes it takes. And you can try to play around with this setup, but basically this is it. So I hope you enjoyed this tutorial. I'll probably see you next time. Bye bye.